Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over question 3 from the 2017 SQA Advanced Higher Physics exam paper, so let's get into it. Question 3 says a student uses a solid uniform circular disc of radius 290mm and mass 0.40kg as part of an investigation into rotational motion. The disc is shown in figure 3a. So there's the disc with the radius shown of 290mm, and we're shown that it rotates about the axis of rotation through the centre. Part A says to calculate the moment of inertia of the disc about the axis shown in figure 3a, and there's 3 marks available here. Well, we just saw that the disc is rotating about its centre, so we're going to use the equation for moment of inertia of a disc from the relationship sheet. So writing down what we know from the question, we're trying to find the moment of inertia of the disc. We know the mass of the disc is 0.40kg and the radius is 290mm, which we need to change into meters. So that gives us 290 times 10 to the minus 3 meters. And writing down our equation, we have I disc equals a half mr squared. Substituting in the numbers gives a half times 0.40 times 290 times 10 to the minus 3 squared. And putting that into your calculator should give you an answer of 0.017 kilogram meters squared. Part B says the disc is now mounted horizontally on the axle of a rotational motion sensor as shown in figure 3b. So here's figure 3b where the disc has been placed on this axle on top of a rotational motion sensor. It then says the axle is on a frictionless bearing. A thin cord is wound around a stationary pulley which is attached to the axle. The moment of inertia of the pulley and axle can be considered negligible. The pulley has a radius of 7.5mm and a force of 8.0 newtons is applied to the free end of the cord. So there's our frictionless bearing there's our pulley and the thin cord which has an applied force of 8.0 newtons. And we're given the radius of the pulley as well. And the rotational motion sensor is connected to a computer to gather the results. B part 1 says to calculate the torque applied to the pulley, and there's 3 marks available. Well, writing down what we know from the question, we're trying to find the torque tau. We know the force F is 8.0 newtons, and the radius r of the pulley is 7.5mm, which we need to convert into meters. So that becomes 7.5 times 10 to the minus 3 meters. Writing down our equation relating torque, force, and distance from the axis of rotation gives tau equals Fr. Substituting in the numbers gives 8.0 times 7.5 times 10 to the minus 3, and putting that into your calculator should give you an answer of 0.060 Newton meters. B part 2 says calculate the angular acceleration produced by this torque, and again there's 3 marks available. Well, writing down what we know from the question this time, we're trying to find the angular acceleration alpha. We now know that the torque tau is 0.060 Newton meters, and the moment of inertia I is 0.017 kilogram meter squared, which remember we calculated in part A for the disc. So writing down the relationship between angular acceleration, torque, and moment of inertia, we have tau equals I alpha. Substituting in the numbers gives 0.060 equals 0.017 alpha, and dividing both sides by 0.017 to get alpha on its own should give you an answer of alpha equals 3.5 radians per second squared. B part 3 then says the cord becomes detached from the pulley after 0.25 meters is unwound. By considering the angular displacement of the disc, determine its angular velocity when the cord becomes detached, and you'll see there's 5 marks available here. Well, firstly we're going to calculate the angular displacement of the disc theta, and then the angular velocity. So writing down what we know from the question, we're trying to find the angular displacement theta. We know the arc length s or linear displacement s is 0.25 meters because that's how much of the cord has been unwound. And we know from before that the radius of the pulley is 7.5 times 10 to the minus 3 meters. So writing down our equation relating arc length, radius, and angular displacement, we have s equals r theta. Substituting in the numbers gives 0.25 equals 7.5 times 10 to the minus 3 times theta, and dividing both sides by 7.5 times 10 to the minus 3 to get theta on its own should give you an answer of theta equals 33.33 radians. We're now going to use angular equations of motion, so writing down our angular equivalent of suvat, we have theta equals 33.33 radians. We then have the initial angular velocity omega naught is 0 radians per second. And that's because we're told earlier in the question that the pulley is stationary to begin with. We're trying to find the final angular velocity omega. We know the angular acceleration alpha is 3.5 radians per second squared, which we calculated earlier. And lastly, we don't know what the time t is. So here we're trying to find omega, and therefore we're going to use an angular equation of motion that doesn't have t in it. So we're going to use the angular equation of motion omega squared equals omega naught squared plus 2 alpha theta. Substituting in the numbers gives 0 squared plus 2 times 3.5 times 33.33, and putting that into your calculator should give you an answer of omega squared equals 233.31. However, remember that's omega squared and we want omega, so taking the square root of both sides should give you an answer of omega equals 15 radians per second. Lastly, part C says in a second experiment the disc has an angular velocity of 12 radians per second. The student now drops a small 25 gram cube vertically onto the disc. The cube sticks to the disc. The centre of mass of the cube is 220mm from the axis of rotation as shown in figure 3c. So there's the cube that's at a distance of 220mm from the axis of rotation. It then says to calculate the angular velocity of the system immediately after the cube was dropped onto the disc, And again, we've got 5 marks available here. Well, to set up the question here, let object 1 be the cube and let object 2 be the disk. And we first need to calculate the moment of inertia of the cube, which we can call I1 since we're saying object 1 is the cube. And we can consider a cube to be a point mass. So we have I1 is what we're trying to find. M1 is 25 grams, which is the same as 25 times 10 to the minus 3 kilograms, and we have its distance from the axis of rotation R1 is 220 millimeters, which converting into meters will give us 220 times 10 to the minus 3 meters. So writing down our equation for the moment of inertia of a point mass, we have I1 equals M1 R1 squared, where we're just using ones here because we're talking about object 1, the cube. Substituting in our numbers gives 25 times 10 to the minus 3 times 220 times 10 to the minus 3 squared, and putting that into your calculator should give you an answer of 1.21 times 10 to the minus 3 kilogram meters squared. We can now use the principle of conservation of angular momentum since we've got two objects interacting. So we can say the total angular momentum before the interaction must equal the total angular momentum after the interaction. And in symbol form that becomes I1 omega naught 1 plus I2 omega naught 2 is equal to I1 omega 1 plus I2 omega 2, where remember the 1's represent the cube and the 2's represent the disk, and omega naught is the initial angular velocity and omega is the final angular velocity. Now we can simplify this by saying the left hand side here will equal 0 since the cube is initially stationary, so omega naught 1 is 0, so that whole term must be 0. And for the right hand side, since the cube is joining onto the disk, we can say that omega 1 is equal to omega 2 is equal to omega since both objects combine. So they must have the same final angular velocity. So rewriting this, it becomes I2 omega naught 2 is equal to I1 plus I2 times omega, where we've just factorised this right hand side since we're saying that this would become I1 omega plus I2 omega, and then we're just using brackets to factorise it, so we're saying I1 plus I2 times omega. And remember, it's this omega here that we want to find. And substituting in our numbers gives 0.017 for the moment of inertia of the disk, times 12, which is the initial angular velocity of the disk, is equal to 1.21 times 10 to the minus 3, which remember we just calculated as the moment of inertia of the cube, plus the moment of inertia of the disk again times omega. And then to get omega on its own, we need to divide both sides by this term here, so it becomes omega equals 0.204 for this left hand side, divided by 1.821 times 10 to the minus 2, which is this term here, and putting that into your calculator gives you the final answer of 11.2 radians per second. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.